Hello everyone. In this lecture, I'm going to discuss what is equilibrium and what is the stability in mechanics. Okay? For this purpose, let us consider this situation. That is, here I'm considering a block resting on a smooth horizontal surface. I'm considering a block of mass m resting on a smooth horizontal surface. What are the forces acting on it? Gravitational force, mg, downward direction, and normal reaction, n, in upward direction. Under the influence of these two forces, the body is at rest. Resultant force acting on the body is zero, because of which body is at rest. So this balanced condition, balanced state, is called equilibrium. This balanced condition, that is this top upward force and downward force, both of them balance each other, because of which body is at rest. This condition is called equilibrium. As the body is at rest, this is called static equilibrium. What is this? What kind of equilibrium is this? Static. So in which resultant force acting on the body is zero and body is at rest. Instead of that, for example, let us consider second case. In the second case, what's happening here is, here there is a raindrop of mass m. So once the drop is formed, what happens? It starts to move downwards due to gravitational force acting on it, mg. As it is coming down, what happens? As it tries to come down, what happens? The viscous or buoyant force acting on them due to atmospheric pressure. What happens? Buoyant force acts on the body in upward direction, whose magnitude is given by V rho z, where V is the volume and rho is the density of the atmosphere and g is acceleration due to gravity. As the body keeps on moving downwards, it acquires some velocity. As the velocity of the body increases, then comes into the picture the force called viscous drag, which is given by 6 pi eta r into small v. This v is volume, this v is velocity. 6 pi eta rv. So this is viscous drag, resistance due to fluid friction. Simply I call it as. So under the influence of these three forces, what happens? This is the only force which causes the velocity of body to increase. These two forces together tries to reduce the velocity of the body. At one situation, when this total upward force counterbalances this downward force, what happens? Body will be moving with a uniform velocity. That velocity we call it as a terminal velocity. In that case, what you can write? 6 pi eta r v terminal. I am calling it as terminal, TR, plus v rho g is equal to mg. Through this, we can write down the expression for terminal velocity. V terminal is equal to what you can write? mg minus v rho g divided by, what is that? 6 pi eta r into g. So remember what's happening here. Here also, in this situation also, the body is in balanced condition. Total upward force is equal to total downward force, because of which resultant force acting on the body is zero. But the thing is, body is moving with some constant velocity. This is also balanced situation only, because of which I call it as equilibrium. But here the body is moving with uniform velocity, because of which I call it as dynamic equilibrium. What is this? Dynamic equilibrium. So all through this, what we understood? Static equilibrium and dynamic equilibrium. In both the conditions, the resultant force, F resultant, is equal to zero. Resultant force acting on the body is zero, as well as linear motion is concerned. If you consider the rotational motion also, resultant torque should be zero. Okay, whatever it may be. So resultant force acting on the body is zero, and in static equilibrium, body is at rest. In dynamic equilibrium, body is moving with uniform velocity. Okay, this is called equilibrium, static equilibrium and dynamic equilibrium. And second thing that I would like to consider is about stability. What is stability? Okay, stability is very much related to this equilibrium only. Because, for example, if you consider a spherical ball, hemispherical ball of radius, let me call it as r, radius of the ball, I am taking it as r. In this configuration, and in the second configuration, the ball is kept like this. In this configuration, this is also ball of radius r only. Okay, now what I'm doing is, I'm considering a small pebble or a particle of mass m over here and here. Okay, now if you look at the free body diagram of this body, what is happening? Gravitational force mg is downward direction, mg is acting downward direction, normal reaction upward direction. Here also mg is in downward direction and normal reaction in upward direction. So because of which total force acting on the body is zero, because of which body is at rest only. Here also upward force, downward force is counterbalancing each other, because of which body is at rest. Now what I'm doing is, I'm slightly disturbing this particle from this position to this position. Slightly disturbed without imparting any velocity. Slowly I moved it and I kept it here. Then what happens? To understand what is happening, simply draw its free body diagram. Okay, so what are the force acting on it? Now the gravitational force is vertically downward direction, mg is downward direction, and normal reaction is always normal to the surface, that is in this direction. Okay, so if you look at this, now the mg and n are not along the same line. So if you extend a line like this, okay, it will pass through the center of mass or the center of this hemispherical ball. Okay, if you consider this angle as theta, then this angle also theta, because of which component of mg is in this direction and its value is how much? Mg cos theta. Okay, then component of mg along the tangential direction is mg sin theta. Okay, so this mg cos theta and n, these two are counterbalancing each other, so it is in equilibrium in this direction. But what is about in the tangential direction? There is an uncompensated force acting on the body, which is mg sin theta. Due to this mg sin theta force, what happens? Body will keep on moving away from this point. Whether you displace this particle to the right or to the left from this position, same thing happens. That is, due to mg sin theta force, which is acting away from this point, body will keep on moving away. So here, once the body is disturbed from its rest position or equilibrium position, this rest position is nothing but equilibrium position, body is not coming back. So here, this equilibrium is not stable. If you slightly disturb it, it is moving away. That's why this equilibrium is called unstable equilibrium. This is called unstable equilibrium. This condition is called unstable equilibrium, in which if the body once disturbed from its mean position, it won't come back to its mean position. It will move away from the mean position. Okay, that equilibrium is called unstable equilibrium. Let us come to this situation. Same scenario. So I am considering particle at somewhat displaced position from its mean position, that is somewhere over here. Okay, if you take this angle as theta. Okay, what happens? Normal reaction now is in this direction and mg is always vertically downward direction. Okay, so if you resolve this mg, okay, along the normal and along the tangential direction, okay, and then what happens? So if this angle is theta, this angle and this angle also theta only, because of which component of mg in this direction is mg cos theta, and component of mg in this tangential direction is mg sin theta. Due to this uncompensated component of mg along the tangential direction, mg sin theta, what happens? Though you displace the particle from its mean position, what happens? This mg sin theta force will make this body to move again towards this mean position or equilibrium position. Am I right? So this is the same scenario whether you displace this block to the right or to the left. Always if you displace the body to the right position, then this restoring force mg sin theta is to the left direction, or else if you displace this body to the left direction, then in this situation mg sin theta force is to the right direction. So whatever it may be, once the body is slightly interrupted from its mean position, what's happening? This restoring force is causing this body to move back to its initial position. So this is stable position actually. If I disturb the particle from its stable position, what's happened? Again it is coming towards the stable position, because of which this equilibrium is called stable equilibrium. This is called stable equilibrium. So, did you understand the difference between stable equilibrium and unstable equilibrium? In both the cases, resultant force acting on the body is zero only. But in the case of unstable equilibrium, if the body is disturbed from its mean position, body is not coming back to this position, it is moving away. That is, this equilibrium is unstable, because of which we call it as unstable equilibrium. But in this case, this mg sin theta force, which is acting as a restoring force, is causing the body to move back to the equilibrium position, because of which I am calling it as the stable equilibrium position. I am considering this third case in which an object is lying on a flat horizontal surface. So mass of the particle, if you take it as m, mg is downwards, normal reaction is upwards. So this upward force, downward force cancel each other, because of which it is again in equilibrium only. But if I slightly disturb this body either to the right direction or to the left direction, what happens? Whatever that is some arbitrary position like this. Here also upward n and downward mg counterbalance each other, because of which resultant force acting on it is zero. So it will move neither to the right direction or to the left direction, because of which this equilibrium is called neutral equilibrium. This is neutral equilibrium, this is stable equilibrium, this is unstable equilibrium.